Today we are going to talk about Bootstrap, which is a method to construct the confidence interval of a parameter of interest. So we first introduced this idea to construct the confidence interval of a mean mu from a normal distribution, also with a known variance sigma square. So we know that the MLE of mu is equal to x bar. So now we denote the error as delta, which is the difference between x bar from the true value. And this quantity here, or delta, follow a normal distribution with mean 0 and variance sigma square over n. So we know that x bar or x come from a normal distribution, and then x bar is just sum of xi over n. And the mean or the expectation of this x bar will be n times mu over n, so it is also a mu. So the difference of that will give us the expectation of this entire quantity here, or the delta, is equal to 0. And then the variance of x bar is that n times variance of x over n squared, because when we take the variance, the constant term will become squared. So that will leave us sigma square over n, and that is the variance of x bar. But this is a constant term, so there's no variance, so the difference of that will be sigma square over n. So this is the distribution that x bar minus mu follows, which is also a normal distribution due to the construction. Okay, and since this follow a normal distribution, so x bar minus mu minus 0 minus its mean over its standard deviation, sigma over square root of n, that follow a standard normal distribution. And then the quantile, or the area under the curve between this quantile and this 0.025 and 0.975 will give us the area under the curve equal to 95%. So basically these are the confidence interval for this quantity here. But we are actually trying to find the confidence interval for mu itself. So we are going to manipulate or rearrange the term here. So we multiply sigma square over square root of n on both sides, and then the difference will be in between these two terms here. And then we finally move the x bar on both sides. We will have mu is greater or equal than this term here. Note that because we have a negative sign here, so we bring the right hand side on the above equation to the left hand side, and then the left hand side of the above equation to the right hand side. So eventually this will give us the 95% confidence interval, since the percent or the probability doesn't change. So this is the 95% confidence interval for the parameter mu itself. So so the logic or the idea is that we construct the distribution of this term here, and then we further expand to rearrange the term to get the confidence interval for the mu, which is our the parameter that we are interested in here, which is also unknown. Okay, so the idea of Bootstrap is come from how or this Bootstrap, the regular Bootstrap. Later we will also introduce another type of studentized Bootstrap. So this Bootstrap is come from the idea or the logic similar to this one here. So in general, for a general parameter zeta, we are trying to estimate the confidence interval for zeta itself. And first we are going to construct or to come from the definition of this parameter delta here. So yeah, this is the confidence interval for delta, which is the area under the curve is 95 for the distribution of delta. And we rewrite delta as the difference between this zeta hat from the true value, the difference between these two. Yeah, so similar idea as what we did here. And then we move this zeta hat on both sides. So we have zeta hat minus this 0.975 on the left hand side, and then zeta hat minus the 0.025. So again, similar idea as what we did above. And then we have a 95% confidence interval for any general parameter zeta here. So here we know that how to construct the confidence interval for theta. The following step is that we need to find the distribution of delta here, and now we are going to find the empirical distribution of delta, or we are going to approximate the distribution of delta. So delta, that by our definition or by our construction, is the theta hat minus the true value. But in general, or we don't know what is the true value for theta, so we use MLE theta to as our as the true value here, and then we are going to use a computer to simulate data, and then we are going to say 1,000 times, and then we are going to estimate 1,000 times of this parameter there, and then we take the difference, and then that will give us like a empirical or approximated distribution of delta. So the process will be, given a data set, we are trying to find, or we are trying to construct the 95% confidence interval for the true parameter theta, but we don't know what the true parameter is, so we use the MLE instead. So that MLE can be estimated from the data, and so we will have one estimation, one MLE estimation of the parameter, and then we are going to utilize the power of a computer to simulate data from our estimated parameter MLE. So we simulate, say, 1,000 sample from this MLE here, and then for each of the sample we estimate a parameter. So that will give us so 1,000 sample will give us 1,000 estimation of theta I, and then we use theta I minus the MLE. That difference we will consider that as the distribution of delta I, of delta, which is empirical distribution and come from 1,000 numbers or 1,000 estimation there. And here I'm going to demonstrate that using a geometric distribution as an example. So this is the geometric distribution for k equal to 1, 2, 3, or positive integer. And then the MLE of this parameter p will be the number of data over the sum of the observation. So that will be the MLE for the parameter p. So here so suppose that this is our observed data set, and we generate 100 observed data here, and then we can using this MLE formula here to find the MLE, and then given this data set, the MLE is equal to 0.33, so which is relatively close to what the true value is. So we sample the data from 0.3 as our observed data set, and this is our MLE estimation for that parameter there. So yeah. And now we are going to construct the confidence interval for the true parameter there. Just pretend we don't know what that value is, and that is from the observation from the real world. Here we just, as an example, we know it's 0.3, but in practice we don't know what that value is, and we're trying to construct the confidence interval for that. Okay, so the idea of Bootstrap, or the procedure, is that we first, given a data set, our observed data set, we calculate or evaluate a MLE parameter. Here we are we're going to run 1,000 simulation. Here I just create a placeholder to store those 1,000 number. So for each of the 1,000 bootstrap length, we are going to run or simulate a data set. So we are going to simulate 1,000 data set, and each sample construct 1,000 random observation. So for each of the 1,000 simulation, we sample 1,000 observation for each sample. So it's 1,000 of 1,000 observation, and then for each of the 1,000 bootstrap length, we sample a data set, and then we calculate the MLE for our simulated data. So this is the sampling data, not the observed data. So here is the observed data when we generate as the observed data, and then we lock it down and as a fix. And also the same MLE here, we lock it down as fix. So we do not change that anymore. And here is the core for the Bootstrap. We run 1,000 simulation, and then we get 1,000 estimate of the parameter there. And then because of our construction, our delta is the difference between the simulation to the MLE. So we take the difference here. So after this 1,000 simulation, we will get 1,000 delta I. This delta I here, and each of the delta I is the estimated parameter minus the MLE that we fixed at the very beginning. So here in this object here, we will have 1,000 number there, and that is the 1,000 estimated delta I there. So we have 1,000 delta I, and from there we use that 1,000 delta I to construct our empirical distribution of this delta here. And then we are going to evaluate or to find the 0.025 and then 0.975 quantile, and then to further construct this interval for our final parameter of interest there. Okay, so after 1,000 delta I, and here these two lines are just to plot the histogram to find the empirical distribution of delta I, and then now we are going to construct the confidence interval for Zeta, which is our parameter of interest, and that Zeta, the confidence interval for that is that MLE minus the 0.975 quantile of that. That's our lower bound, and the upper bound is also MLE or MLE minus the 0.025 quantile. So that's what we are doing here to construct the confidence interval, the lower bound and upper bound. Note that this is 0.975 and this is 0.025, and then we report the confidence interval for that. So now we call this function here using our data, observed data here. This is locked down, and then inside this function here we generate 1,000. We do 1,000 simulation. And here is the empirical distribution of delta there, and then the value that we want is that the 0.025 percentile and the 0.975 percentile. So that means that in this empirical distribution, which is construct from the 1,000 simulation, the area for here is 0.025, and the area here is also 0.025. That will give us the area in between 0.95. So here is the confidence interval for the parameter of interest for the Zeta there. And actually we know what the parameter is because we are using a sample here as our for our example, which is 0.3. But as you can see that our constructed or the estimated 95% confidence interval does not cover the true value. But in reality, we don't know what the true value is. But here we're just basically kind of cheating. So we know it's 0.3, but this confidence interval does not cover the 0.3. So in reality, whenever we construct this confidence interval, we still need to decide whether we trust this confidence interval or not. So in this case, actually it does not cover the true value. So but we don't know what the true value is. So yeah, we probably would need to use some domain knowledge or some expertise to decide whether we trust this or not. So in this case, we should not trust. But this is just a 95% confidence interval for the parameter there. Okay. So that's just one way to construct the 95% confidence interval Bootstrap. And now we are going to introduce another studentized Bootstrap to construct the confidence interval again for the parameter Zeta there. And we are also going to use the same example. So the true value will be 0.3, and now later we can see that this one actually we can see whether it covers or not, does or not cover the true value there. So the studentized Bootstrap the idea is come from here. So we introduce that from the confidence interval, again, of the mu from a normal distribution. But this time we pretend that we do not know the variance sigma squared there. So in the previous above example, or the logic is that we assume that we know the variance of sigma. But here we now assume that we do not know the sigma anymore. So from an unknown variance, and in that case we will need to estimate the variance in order to find the confidence interval for this mean. So we start from this equation here. So x bar minus mu over its standard deviation. So this term, there's a theorem, or by construction, this one follow a t distribution. So for this one, for a parameter that follow, for a variable that follow a t distribution, so in between these two quantile is equal to 0.95. That is just a definition. This one follow t distribution. So in between these two quantile, of course, it is going to be 0.95. And now we are going to multiply by this xs. This is the sample variance that we estimated from the data, because we don't know what the true variance there, sigma square, anymore. So we use the data to estimate this s, and we multiply that on both sides, and then we move the x bar as well as what we did as above. So we have x bar minus this quantile 0.975 multiplied by this estimated standard error as the lower bound, and this one minus, again, is minus this lower or the 0.025, and then multiply by the estimated standard error, and that will give us the upper bound. So this is the 95% confidence interval for our parameter of interest. So above we use the normal distribution, but once we do not know the true variance, well, we will need to use our sample to estimate that, and that will give us this this quantity here follow a t distribution, so it does not follow a normal distribution anymore. So that's the underlying logic, or the idea for this studentized bootstrap. Okay, so now again we start from this equation here. So for the distribution of delta in between these two quantile, we have 0.95% or 95 in the center mass of this distribution of delta, and this delta here is not the difference between the true and the estimated parameter anymore. It is actually the true minus the estimated parameter minus the true over the estimated standard error. So we define that as our delta, and now from here we can construct the confidence interval for our parameter of interest in general by that. So similar idea. You can see the similarity as this example for the normal distribution, but now we are just going to talk in general for any general parameter theta there. So this will be the confidence interval for this parameter theta, and now again we are going to return. So we are trying to get what is the or the distribution, or the empirical distribution of this delta, or this term here, delta or theta hat minus theta over estimated standard error. So you can think of this that so this part is come from data, and this part is also come from the data. So we basically we introduce some more information that come from the data into this quantity here to estimate the distribution of this delta here. So now again we return our final procedure is to estimate or to evaluate the approximated or empirical distribution of this delta here, which is this quantity here. So now we have the same idea back to our original bootstrap method there. Okay, so to find the empirical distribution of this delta, we will need not only the MLE for this theta, but we also need the estimated standard error And for the estimated standard error, we are going to use the asymptotic variance of the parameter MLE, of the MLE estimation. So the parameter MLE follow a normal distribution centered at the true value P and the variance of 1 over n multiplied by the Fisher information of the parameter P. So this is the variance. So the MLE parameter follow a normal distribution and a normal distribution P and variance 1 over n times Fisher information. So this is the asymptotic distribution of the MLE parameter. And now we are going to evaluate this this variance here, and this variance come from the score function and the Hessian. I will make another video talk about this information or the maximum likelihood in another video, but this will be the asymptotic variance for our MLE parameter there. So now if we use the MLE minus this mu minus this P and then over this estimated standard error, that will become our the quantity here, and furthermore that would be the distribution of the delta. So again, P MLE minus the mu, which is P MLE minus the mu over the estimated standard error. So over the square root of this this term here, that will be that will give us the distribution of this delta here. So that's the idea to estimate this delta, instead of in the previous example it is just the difference between the two parameters there. Okay, from this construction we are going to go through the code. Okay, so yeah, again here pretend that as our observed data set. We observe 100 data, and then we are going to run 1,000 simulation there for the Bootstrap. Again, this is the function. Given the data, return the MLE. And here is another function. Given the data, return the asymptotic variance. This is just our code for this one here. And then the P here is replaced by the MLE there. So all the P here is we replace that as MLE. So from the data, we can get the PMLE, and then from there we can get the asymptotic variance of the parameter P for the parameter MLE. Okay, so we define two functions. One return the MLE, the other one return the asymptotic variance, and then the square root of the asymptotic variance will be the estimated standard error there. Okay, so now we work on the studentized Bootstrap. Again, we are going to run 1,000 simulation, and in each of the 1,000 simulation, we are going to generate a sample, and the sample size is 1,000 as well. So it's 1,000 of 1,000. So it's 1,000 sample of 1,000 data point. Okay, so now the function of studentized Bootstrap input is the data. So we find that the MLE, the PMLE, and then the estimated standard error. Once we calculate these two terms, we lock down and then we fix those two. So we pretend that as the MLE, and that comes from the simulation, and this estimated standard error also comes from the simulation, from the Bootstrap. Okay. So when these two are calculated, we lock down, and again, this is the placeholder. And here is the part that we run the Bootstrap simulation. So for each of the 1,000 simulation, we generate 1,000 sample or data point, and that is our sampling data. And then we calculate this P star as the MLE of the sampling. So that is this theta hat there. And then we use that theta hat minus the MLE that we locked down at the beginning, and then over the estimated standard error from, again, this one also from the simulated sampling data. Okay, yeah, so the estimated standard error star is also the square root of the asymptotic variance from the sampling data. So from the sampling data, we get this P star and the ESE star. So that is here. We get that from for each of the sampling data. We get that and we get the denominator. And then we are going to construct this delta here by using the MLE of the sampling data minus this true zeta, which is what we locked down at the beginning, over the estimated standard error from the sampling data. That is what this part is doing. And then we return that for 1,000 times. So we run this, we construct this 1,000 times. And then we use that delta I, 1,000 of the delta I, to construct our empirical distribution of delta. Here are the two lines that we plot the function, plot the distribution of delta. And then we used the delta I, and then using those two quantile multiplied by the ESE. This is what we also locked down at the beginning, which is defined by here. So for the simulation, what we did 1,000 simulation to construct this. So this ESE will not be different. Will be different from this ESE when we calculate the confidence interval. So this ESE will be the one that we lock down, and this ESE will be the one that we evaluate from the sampling distribution. And eventually, we are going to construct the confidence interval for the parameter zeta using this equation here. So this is the lower bound, and this is the upper bound. Zeta hat minus the empirical or the quantile for our empirical distribution multiplied by the estimated standard error that we locked down at the beginning. So this is what we are doing here. This is the quantile, the 0.975 quantile from our empirical distribution of delta multiplied by the ESE, and then we use the PMLE. So this is what we locked down at the beginning. This is what we locked down at the beginning. Only this part is what we get from the simulation. And then we do that and that to construct the confidence interval, lower bound, upper bound, for the parameter zeta. So that is the last step here. And that will give us the confidence interval, 95% confidence interval for this parameter zeta. And here we also return the confidence interval from the asymptotic variance. So this is just come from the Q norm multiplied by that. So similar idea from the previous example. And this is the studentized bootstrap. And here is the empirical distribution of delta, which is constructed from our simulated, from 1,000 simulated delta I. And here is the two quantile there, 0.025 and 0.975. And here is the two confidence interval. So one is the studentized bootstrap. So now you can see that this one cover the true value there, which we already know is 0.3. And this is the asymptotic variance. That is the confidence interval from the asymptotic variance, which is the difference is that we don't need to run the simulation anymore. We just use the Q norm or the Q or the Z from the normal distribution multiplied by the asymptotic variance, which is equivalent to what we to this part, what we locked down given the data set. So we can see that both of the confidence interval, the studentized confidence in bootstrap confidence interval, and the asymptotic variance, the confidence interval, all cover our true parameter there. So here basically here in this example, I provided two ways to construct the confidence interval using Bootstrap. So one is the regular Bootstrap and then the studentized Bootstrap. And here is the third way to construct the confidence interval without using the power of a computer. So we don't need to run simulation anymore from the asymptotic variance, and then using because it follow a normal distribution here. So that's why we can use the Q norm or the Z quantile to evaluate the parameter P there. So basically, here are three ways, and two of them is by using the computer to run simulation to construct the confidence interval, and this is more of a theoretical from the asymptotic variance to construct the confidence interval. So here are the basic idea for the Bootstrap to construct the confidence interval and for our unknown parameter. but we still need to decide whether we trust that confidence interval or not. So, but in reality, we don't know what the true value is, so we don't even know whether this covers the true value or not. It's just 95% confidence that it covers the true variable given the data set. So using the information that we have at hand to do that. Okay, so yeah, this is the idea for the Bootstrap.